Okay, thank you. Today we're going to talk about some performance considerations for when you're working with MongoDB. So the first slide we're going to go. Let's look at the relational databases and what is the difference in SQL and NoSQL databases. So relational databases are based on the principles put forth by Dr. Cord back in the 1970s. The data are normalized, stored in relational tables, which are logically connected through primary foreign key relationships. So an SQL is based on set theory to manipulate the data and make a good choice for the applications that involve several transactions. So it's a relational databases have been from a long time. We don't have to talk much about it. But just to know that they are primarily driven by data, structuring data into tables and relationships and the normalized models. So you have to define the schema ahead of time and structure the data in advance. And one of the disadvantages that was faced is that this provides inflexibility for your schema for any database changes, right? So it makes it a very slow process to make changes and involves significant downtime. So in a non-relational database, it is a database that does not use these tabular structures of rows and columns, right? Rather, its storage model is optimized to the type of data it is storing. So NoSQL databases usually doesn't have a predefined schema. This makes it easy to make significant application changes in real time. So in a SQL database, if you're talking about some dissimilar data, like, as we talk about structure, unstructured, predefined, and dynamic schemas, if we talk about a customer and a product, right? In relational world, it is stored separate, that they have their own entities and relationship. But in NoSQL, we can store them together using an unstructured storage format, right? So, and again, the other difference is the acid and base consistency. So acid compliance is one of the strengths of the relational world, that it guarantees validity of transaction, even in the face of errors, some failures, or any kind of shutdown or any problems, because of the atomicity, consistency, and isolation durability that is offered with the ACID transactions. So the NoSQLs are mostly basic. So the base says that base says basically available. So it says guaranteed for query. It's a soft state, which means that values stored in the system may change, don't have to be write consistent, and eventual consistency. So initially you will not have consistency, and ultimately you'll reach consistency. So after every transaction, it may not be consistent, but at the end of the day, it will be consistent. But that is not acceptable if you're doing a mission critical system with a transactions that are critical to the business. So the other thing is the scalability. So that is one thing I would say is considered as a big drawback of NoSQL, that about ACID consistency. So another thing is scalability is SQL databases are designed to run on a single server to maintain the integrity of the data. So it's not easy to scale. That's how they are built by design. And but they scale vertically in the sense that you can add more resources like CPU, RAM, or SSD. For NoSQL databases, on the other hand, they are scalable horizontally. So you can add more servers to NoSQL databases. You can build a cluster, and it is something similar to building more floors to a building versus adding more buildings, right? The latter can ultimately become larger and more powerful, and that makes NoSQL databases a preferred choice for large and even changing data sets. So now the question comes, when given these differences between SQL and NoSQL, when to use it, right? So big data is the real one of the key motivators for NoSQL. In relational databases, traditional databases, NoSQL, there is not much choice, right? This is what drives the popularity of NoSQL databases like MongoDB, CouchDB, Cassandra, and HBase. And with rigid models, the scaling up is tough. So if you have a growth, you're planning for growth and planning to store large volumes of data, a NoSQL database sets no limits on the type of data you can store, and you can allows you to add new type of data as you need, as the structures change and the data grows. And cloud-based storage is an excellent choice for such a design, because the data can be spread across multiple servers to scale up. So because the horizontal scalability of NoSQL databases, it makes a good choice for a cloud computing and storage. So due to agility, if we talk about agility, as we discussed prior, due to the rigid data models needing to make updates or changes to the data structure for the relational databases is a very slow process. So NoSQL data doesn't need to be prepped ahead of time. It can do agile, rapid developments. And if you look at NoSQL database types, we have popular, 4 of these are quite popular. Key value. A key value stores values of one type of binary objects and are accessed by a key. So just as an example, the key can be, applications have complete control of what is stored in this value. You can change this value. They're highly effective for application scaling that deal with high velocity non-transactions data. So if you look at it, the key value databases follow an object-oriented schema type. And if you look at columnar databases, looks at how, just an example, how it stores the data. This data storage is in columnar rather than rows. So columns related to data are grouped together. So a query can retrieve related data in a single operation because only the columns associated with the query are retrieved. So in an RDBMS, the data would be different. Different rows stored in different places on disk requiring multiple disk operations retrieval. So depending on certain queries, let us say you want to query all the employee names, employee numbers. So having this columnar association, the IO profile is lower and overall storage footprint is lower, and the columnar databases has the ability to compress data. So in certain situations, columnar databases are more efficient to retrieve and store data. And the third is the document databases. This is where this is MongoDB is a document database. So there's similar to key value, as you can see here, but instead of a value, it stores a document in the value. And as you see a structure here, each document can have a different structures. So the design of the data in a document database takes a semi-structured fashion like JSON or XML. And then if you go to the fourth one, which is popular graph databases. So graph databases use graph structures to store, map, and query relations. So data that's interconnected and best represented as a graph. And graph databases focus on how data relates to other data points. So a data from graph store a link between data sets called edges. So the links are edges, and the edges are represented as a graphical representation. And so it is just meant to connect the dots to see the whole story, to just have a visual representation of how the data looks. So a node is a representation of individual entity to track by a graph database. So it's more like concept of a document in the document store. And a property is a relevant information related to the individual nodes. And edges are relationships, an edge representation of how two nodes are related. So what we can say is that while key value is highly unstructured, comparing these 4, the document store have a semi-structure, because you see each document comes with a metadata that provides a degree of structure to data. And if you go to graph database, it adds an extra layer of highlighting the relations between the individual documents. So we have so many choices, and the question is why MongoDB? So MongoDB provides certain features. It offers the flexibility, like because it's a schemaless or non-relational data store. So it gives a huge, huge degree in storing various data types. What we call versatility, and access them. You can access them whenever you need. So due to the dynamic schema, basically, you can try new things at a lower cost. So you don't have to worry about, just like a relational world, preparing the data. If you want to do experiment, if you want to try analytics, you don't need to have build a model and do all those really normalization. So preparation is less. So how also it's easy to integrate in the development pipeline. Another flexibility is that, so you don't have to learn about database technology, SQL. You can start right away. JSON structures are simple, and you can just, it doesn't require to be normalized. And the second feature we see is the sharding. So sharding is nothing but distributed computing. So you can spread the data across multiple servers. That makes it cloud friendly, and scales up easily by adding more servers, right? Auto sharding is a feature that data shards into rebalances automatically. So what happens, each shard holds a portion of the data, and they work as a separate databases. The collection of these shards looks like a logical single database. So it divides the data between different machines to improve the performance to under read operations. And the performance, so the storage, access, search, and analysis of the massive amounts of data you can do at speed. So the lack of a relational structure means that submitting a query requires less processing power to search and retrieve. Performing joins in relational world, joins are the main things that drive the how we can relate and bring the data together. So that is an intensive process, and that could have a negative impact on performance. So from a denormalized document, you can just bring the entire document, the joins are reduced, and the performance improves. And the cost effectiveness, right? You don't have to, it is open source, mostly it is free, and it's supported in multiple languages. So it offers both community driven open source, and also it has a premium enterprise edition, but still it is very cost effective. And a transaction integrity, MongoDB supports multi-document ACID transactions. So one thing we mentioned about ACID transactions, the MongoDB provides ACID transactions starting with release 4.0. So aggregation framework it supports aggregation frameworks that you can perform a variety of operations on grouping the data and returning a single result. So there is an aggregation pipeline framework that supports, you can have a series of data transformations. So you can have several stages. From the first stage, the collections of document as input, and then from that, the subsequent stages takes the output as input and do the transformations. And grid file system, it's something interesting is that MongoDB can also be used as a file system with load balancing and data replication features, using multiple machines for storing files. So the grid FS feature divides files into smaller parts and stores them on separate documents. And then failover and automatic failover. So the fault tolerance provides automatic failover. Data is distributed and replicated onto multiple nodes. So you have one primary node, one or two secondary nodes. So when one of the set members can't reach the primary instance for more than 10 seconds, what happens is the replica set will automatically get elected and promote a secondary instance as new primary. So this auto fault tolerance features, because of replication of data and how the data is managed, makes it, provides a very good fault tolerance. Indexing. So indexing, you can index these documents in Mongo. You can have primary and secondary indexes. The database engine can use a predefined index. It can map the document fields and can can provide the information to the engine on what documents the query statement can bring and improve performance. So MongoDB also supports ad hoc queries by indexing based on documents and use a unique query language. So these are some of the features. So now let's look at some of the use cases of Mongo. So if one is, we mentioned big data, right? MongoDB's NoSQL or non-relational structure is perfect for the big data, which has volume, variety, velocity, and veracity, 4 V's of big data. So any use case that can require large volumes of high-speed data, logging and aggregations is a perfect fit for Mongo. Analytics. So one of the Mongo's strengths is the big data analytics. And we can have e-commerce solutions like, online store or powering an online store, the content management, mobile development, real-time integration. So analytics and data visualization, right? Event-driven streaming, data pipelines, text searches, geospatial search, in-memory performance, global replication, all these to accomplish for an RDBMS, it requires an addition of a lot of complex technologies and separate integration. So for MongoDB, this is all comes with it for real-time data integration, to support real-time data integration. So these are some of the areas where MongoDB is a great fit. So if you look at the 4.2 features of Mongo, it provides distributed transactions, which says basically 4.0, we mentioned that it provides ACID compliance. So the multi-document ACID transactions is a feature that provides a consistent view of data across the replicated sets and enforcing execution to maintain data integrity. So 4.2, it extends this multi-document ACID guarantee to shared clusters. So giving that an easy way to address a complete range of use cases by enforcing transactional guarantees across high-scaled global applications. So as told, the ACID transactions was a big strength, and 4 and 4.2, it takes in more advanced state. And client-side field-level encryption, MongoDB introduced in 4.2 the capability to select, encrypt, and decrypt document fields in the application before data is sent to the database. So application level encryption of fields prior to transmitting data over to the server. So only application with access to the correct encryption key can decrypt and read the protected data. So using client-side field level encryption to protect data prior to being written to the server mitigates the risk, a big risk of exposing the data in the event of network or disk encryption bypass. So this is the client level security encryption is a very good feature. An on-demand materialized view. So what happened with the 4.2 is that if a new collection is the output, if the transaction resulted in a new collection, it creates the output. But if it is an existing collection, needs to be updated, it used to overwrite. So with the aggregation output. So the new feature, which is $merge, they have this feature which can update the existing instead of overwriting, right? So this enables to create on-demand materialized views where the contents of the output collections will be updated each time the pipeline is run. So you will have these on-demand views because the pipeline can update on an ongoing basis. And the other one is Kubernetes. As you may know, Kubernetes is the industry-leading container orchestration platform. So it provides you the consistent automation and management experience anywhere from on-premise infrastructure to the public cloud. You can use Kubernetes to manage full life cycle of your MongoDB cluster. And now for 4.2, Kubernetes is now certified to production deployment. Wildcard indexing is that allows you with, rather than try and second guess every access pattern in advance, because we are dealing with a lot of unstructured data, wildcard indexes can filter and automatically match fields at a document, sub-documented field or an array collection level and index anything that matches. So it is enables much simple schema design for certain cases like polymorphic patterns. So for performance consideration, there are many things, but we look at now at 3 factors, right? How we can improve performance using the schema design, indexing, and sharding. So let's start with schema design. So schema design, MongoDB provides, and schema design plays an important role in optimizing the performance. So there are usually three options: embedding, linking, and bucketing. So in the relational model, if you look at it, we have entities and relationships like primary and foreign key to organize the data. But in NoSQL, MongoDB, document design, we do not have these primary foreign key relationship. The embedding, linking, bucketing, these are the choices provided to organize data and normalize and denormalize in a fashion similar to relational models. So let's look at one scenario that says, let's say I have a, just a hypothetical, just to make for understanding. Say, let us say we have a product that can have many orders, but an order is placed for a single product. So when you place an order, you can only place an order for one product. So just we wanted to see the one-to-many relationships here, how it is handled. So if you look at the JSON structure for it, you have just like product document, product document 1 and 2, and order documents 1 and 2. So these are simple product and order JSON structures. And embedding, how the embedding works is that you just take this order documents and put it in the in the product document. So what we did here was we created one single document by embedding orders into products. So this improves your performance because you're not maintaining two separate documents and accessing two separate documents when you're querying for related information. Now what happens when the many sides of the one-to-many relationships keeps growing? So you can have a product keep having orders, and the product is one, but the orders can be many. And as it keeps growing, if there are too many orders, the embedding is not going to work because the document will become too large and create write performance. So MongoDB, we have to copy the document to the new location and update all indexes. This causes write performance because there's a lot of I/O involved. So, and also the document can hit the maximum document size stipulated by Mongo. Mongo stipulates the document size to prevent document to grow too large. So we may hit that if you keep adding the embedding orders to the product. So too large document, you can have write performance. So in that case, what approach you can take is that you can do linking. So in linking, what you're doing, it's similar to a foreign key relationship, but remember, you don't have the constraint. So we've added product key. If you look at in the orders, you have ordered product key, you added product key, and in the order document, you added product key. Just two examples here. When we do that, what it does, it creates the link so that when you query, you can relate an order to product using the product ID. So instead of embedding, we kept them separate, but and avoided one single document to grow too large, causing performance issues. But now look at what happens if the number of orders keep growing. So we overcome the write performance, but now if we can have read performance because you're creating every one document for each order, and there could be thousands and thousands of documents, and that need to be scanned for queries depending on how the order information required is being queried. So what you do in that case is, so too many documents to scan, you will have read performance. And we have an option where what we can do is bucketing. So if you look at how we embedded before, we take that, and what we're doing here is we do bucketing. If you look at it, we added start date and end date to it. So that what happens is we group the documents. Is similar to embedding, but we set a limit here. We're setting a limit. So we added the start date so that you only have in a document orders for certain time range. So once that time range is over, it creates another document for that. So we created bucketing. So by multiple buckets of the documents, we balance this the set number of orders. So when we split the document into discrete batches, at a time, a single read will only fetch a limited set of orders with efficient paginations. So this is some of the ways you can look at how we can improve the performance. And now let us look at a more common scenario, which is looking at a product can have many orders and an order can have many products. This is usually what happens. There's no limit, right? Because a customer can place as many orders and he can put as many products in the cart. There's no limit as long as he can pay. So this scenario is called in a relational world many-to-many relationships. So in MongoDB, you can do this by having two-way embedding. So in two-way embedding, what you're doing is each product document will list all the orders of the product, and each order document will list all the products in the order. So that way you're linking the documents and able to perform the queries in both directions. So two-way embedding can also be optimized by using bucketing, right? But one thing we need to remember is that two-way embedding works best if there's a good balance on the both sides. That means you have products having a lot of orders and orders having a lot of products if there is a balance. So, so even though if it's a good balance, let us look at a situation. We always have to look at an exception situation. So for example, you have a warehouse that sells products. So you have, the usual number of orders, average orders, order fluctuations. But there could be an exception that, for example, you can have, suddenly you get 10,000 orders for toilet paper, right? So you got an exception. So how you handle this? You create an exceptions flag, right? You create an order exceptions flag in a product document, so that when you hit 1,000, you can populate this exceptions flag and move further orders to another document. So linking these products, so another document for further orders. So this allows you to stay in the max document limit and also split access to orders to take care of exceptional situations to maintain the balance. So now this is for exceptions. Let us say you have continuous imbalance, right? What I mean is that it could happen that a product can have many orders, but the number of orders keep growing and growing. Whereas an order usually have a limited number of products. So in this case, we embed the references in one side of the relation. We can optimize the read performance. So we just left the product as it is. We didn't embed the orders in it, but in the orders we embedded the products. So that way we can control the growth and also optimize the raise relationship. So so you consider if your application is read intent to or write intent to, look at that feature too, how to design the schema. If you have consider pre-aggregations, right? So the pre-aggregations is about think about those which are required again and again. So if you have here we have added some count order quantity, count order numbers. So what we're doing is we are incrementing is whenever new order is added to the product, right? And counter is maintained in the rolling order numbers, revenues, or whatever aggregations you need. So what happens is in case you require this, it's quickly retrieved rather than having to compute all the time. So what's happening in this case is the number of reads are much more than writes. So you're writing only when there is a new order for a product, right? But the applications are constantly querying and requiring the data. So if you make these pre-aggregations in the right side, when you actually adding the data, what happens? It makes it faster because by computing during writes, by incrementing the counters, and so we avoid having to repeatedly compute intensive aggregations when we do the reads. So another thing in the MongoDB, the joins happen on the application side, not on the server side. So since you're joining on the application side, it can impact the performance if there are a lot of joins to the data trips and joins. So we got to reduce that. So consider denormalizing the schema accordingly. So to reduce joins, one thing you can do is look at the polymorphic patterns. So what it means is when all documents are similar, right? May not be identical and structure wise, but if they're similar, they fit into the polymorphic pattern. So grouping them into a single collection to reduce the joining of the queries. So for example, if you look at the product catalogs, each product has different attributes. Pencils, for example, pencil as a product is very different attributes than hand sanitizer as a product, but they have many attributes that are common too, right? So if you're required to join these product data queries, using the polymorphic pattern, grouping the products as a collection, as a single collection helps to improve the query performance. So now we talked about collections, but what happens within the document? Within the document also, there can be similar patterns, right? For example, if you look at the hand sanitizer, for example, right? They may come in 3 flavors. So we can say that it has alcohol percentage mild as 40, 60, and 80 percentages. It's 3 categories depending on what is the alcohol percentage. So you can, as you see in the bottom, what we're doing is that we are grouping these attributes together as a key value pair, right? So that we can create an index and it makes it efficient to query. So consider that where you have that relationships within the document, similar relationships. So another way to reduce join also is by denormalization, right? It's quite popular. So identify that data exists separately in 2 different documents and collections, but queried frequently. Look at your queries and then duplicate the data to avoid joins. So for example, you find that there is frequent need for information on the product description when querying the order. So instead of every time taking the product item and getting the description from the product document, we can add this description to the order to avoid data joins. So the example, it shows 2 examples. One, it shows as a description field. Another shows as an array of structures. Depending on how data is, you can have both ways and whichever way. But the concept here is that duplication sometimes gives you performance. Another area we are focused with multi-joints is about when you have a subcategory relationships. So the product hierarchies, for example. So the hierarchies exist all the time. Let's say, for example, for the hand sanitizer we took, you can say the antimicrobial has sterile, disinfectant, and sterilizer subtypes. And then within sterilizer, you have limited spectrum, broad spectrum, and hospital grade, right? So when you have these things, we can have a product hierarchy improves the performance because the hierarchical structure will be needing multi-joins to trace categories and subcategories. If we have a query that requires order information for the sanitizer category, so if we're having this structure inside, we may be denormalizing and duplicating the hierarchy in each of the product document, but it is worth the effort if you often have queries requiring hierarchy multi-joins. So if you have hierarchy multi-joins, here's an approach. So another thing we need to look at it, Mongo architecture, like many databases, tries to use RAM efficiently to avoid disk access, right? It is all systems do that. We know that because accessing RAM is much faster than reading the disk. To achieve this, what it does, it loads most frequently used documents and prints to memory. So the entire memory management and Mongo architecture is a topic that we cannot take it today. But the important point for us to remember is to consider is that how we design our schema to reduce disk swapping, right? Let us take the example of product document. When let us say the customer asks questions about the product and the product experts provide the answers, we decided to store that information in the product document. So what happens when a query for the product comes, it tries to load the entire product document, including all the questions and answers into the RAM. So if we look at it, the product information, like product specifications is more frequently required than the question and answers. So we are finding here certain set of data within the document is less frequently required compared to other set. So based on the usage preference, we can split this into 2 collections, a product collection and a product question and answer collections. So what we did was that we in the product collection, we just kept the top 5 questions and all the remaining questions we moved into another Q&A question, right? Q&A document. So now let us look at another consideration we need to look at is what happens, okay, we are collecting all the questions and answers. We have
Padmesh,
yes.
I need you to finish up, please, because we have another speaker.
Okay, sure. So so these are the versioning is another consideration. When you have too many records growing up, you can version. And then let's look at MongoDB indexes. So what we can take, so let us look at briefly on optimizing indexes. We talked about various ways how we can optimize, how we can design the schemas. So there is no exact formula for schema design, right? We ran through few scenarios on how we can control the MongoDB design patterns to improve performance. So one thing we need to note is schemaless doesn't mean that you can just dump everything and get performance, right? So you can have schemaless means you can have a document with strings, structures, nested structures, arrays, structures, and you can have a lot of nesting. But schemaless doesn't mean that you don't need to design the schema. If your system is performing poorly, first look at the schema, how we can design the schema, use these techniques to achieve high performance. So in consideration of time, let's briefly look at the indexes. These are the indexes that Mongo provides. So I'm going to skip these indexes and go to sharding. We will come back to indexes later, probably in another session. But if you look at sharding, so sharding is nothing but horizontal distribution, as we discussed before, right? So we can is the database partitioning similar to the concept of database partitioning, but it is more automated in MongoDB for data balancing. So why shard means there is memory constraints. Your process can access the pooled RAM. IO constraints. By sharding, you are not limited by a single server. Increased availability because of distributed processing. The cluster has even one node fails, you can have uninterrupted cluster availability. Growth. So once you set up the sharding, it's easy to grow by simply adding more capacity. So just the sharding, if we just look at this topology, the Mongo's router stands in between the shards and the application, in the sense that your application, it looks like a single server, and the Mongo's takes care of all the routing queries, fetching data from the shards, and all kind of complexity behind. So a shard key design, let's talk about some of the things that you need to consider when you design the shard key. It's very important. So look at the cardinality, right? Partitioning data into chunks. When you set the key, shard key, that's what it does. It partitions data into chunks and distributes across all shards. So if you choose a high cardinality shard key, it creates unsplittable chunks that cause uneven load distribution across the shards. So a chunk, we should look at it as a logical concept. So by chunk does not mean that it is physically contiguous on the disk. So we need to keep that in mind, that if a key has n values in a collection, you can only have n chunks and therefore n shards. So for example, if your shard key is the city where the customer made the order, right? Then it could happen that you have a large number of orders in few cities. And because the large chunks are based on the city, these chunks are unsplittable based on the shard key you provided, because you set that city, and cannot be moved across the cluster, causing a load balancing issue.